video 8 of 8 for day 8 sets. You'll be relieved to know that the set of videos for sets is finite. This is the last one. Congratulations, you've made it to the end. I just want to go over how you can use binary search trees to implement sets. So the search property we defined in day 7 has us keeping the list in a certain sense sorted. The root node is greater than everything in the left and less than everything in the right. And those inequalities are strict, right? There are no duplicates anywhere. This is reminiscent of the sorting property we had for the second list invariant, and now we're doing it for trees. Because they're trees, we have slightly better ways of traversing them. For example, checking a membership in these sets means only looking in one branch of the tree, which is slightly better than our list implementation where you have to scoot along and find it. So we have just a couple of simple exercises here for you. Simple meaning that you shouldn't have to write a lot of new code. Our solutions for these are often a single word, right? We just say, oh, it's this function. So I really counsel you to look at stuff from day 7. Names from day 7 will just apply directly here. And certainly for the first few problems, your answers can be very simple. We just want you to recognize that some BST operations you've already defined do what we want them to. Okay, so here's what they are. What would you define empty nat set as? What's the BST representation of an empty set of naturals? What about insertion? If I have a natural and I have a set of naturals here, now we're in some module where it's binary trees of naturals where we're maintaining the search property, what operation do I want to insert something into a set? Okay, and then lastly, what about union? How would you define union? You could try to be efficient here. I'm going to counsel you to not go crazy, right? If it's more than 5 or 6 lines, you've just gone in too deep, right? I really, really, really want to counsel you against a thing that I've noticed a lot of people doing in their source code, which is sort of thinking ahead in their recursion. Your recursion should be very local. Do the simple thing. It'll be all right. And that's basically it, right? If you have questions about how binary search trees might apply, what I would ask you to do is go look at all the things that we said count as BSTs and ask yourself, if I did an in-order traversal of these, would I get out a sorted list? Would that list be a good list-like representation of a set? And once you've done 3 or 4 examples, I think you'll start to see why binary search trees become such a good representation of sets. That's all of the detailed stuff I need to say about binary search trees here. There's other notes that I think are worth mentioning. In particular, in the world, binary search trees on their own aren't exactly what people use to implement sets. The concern with a binary search tree is it can become imbalanced, right? A binary search tree where everything is a right child, well, that's kind of just a list, right? If you're never using the left children, then you're not going to get much advantage out of any of the fancy tree cutting stuff that we do where you only have to look down one side because everything's on one side. So in practice, what people do is they have a variety of operations for rotating and balancing the tree to keep your tree kind of more or less balanced. And then there's more advanced tree algorithms that sort of maintain something like the search property, but a little more intensive in an effort to sort of keep track of things better. So names of these that you might hear about and are nice to have kicking around the back of your head, but are not at all important for us right now, are things like AVL trees, finger trees, red-black trees, B trees. I'm sure I'm leaving some out. Min heaps and min-max trees. All of these are things that are ultimately variations on search property invariants or related invariants on trees that aim to sort of just do a little bit better in practice. I'm not going to go over them. You might hear about some of these. You'll probably talk about heaps in CS62, but it probably won't go much deeper than that. Good to know about these names. The Wikipedia articles often come with good examples if you want to learn more. Okay, that's it for now. I hope today makes sense. I realize this is a lot of videos, but it's not too much work in terms of the number of exercises. Any problems? Take it to Zulip. I'll see y'all soon.